Hello. In this video, I want to talk about the foundations on which we do all of our mathematics. So, math, the way that I view it, is all founded on set theory, in particular, what is generally called the ZFC axiom system. So this is Zermelo-Fraenkel plus the axiom of choice, and this is all founded on first order logic. So in this video, I want to explain what I mean by uh, mathematics. Mathematics is constructed out of statements, and these statements are about these things called sets. And everything in mathematics is a set, or a statement, or a predicate. I want to explain what these things mean. So because this is the sort of foundational video, there's nothing for this to be founded upon. So I need you to sort of accept some of the things I say without justification. So I want to explain what I mean using English, and I will list a bunch of axioms, which are things I want you to essentially assume are true. And then all the other math that I ever do will be based off these things, and I will make no more assumptions in other videos without justifying them based on the content of this video. I might occasionally make a video where I assume some knowledge, which I have not made in other videos yet, but the idea is I want to make videos justifying everything that I say in all my videos. But this is the sort of foundational one, so I will say some stuff without proof in this video. So what do I mean by these things? Um, so everything in math that we get used to later on are actually what we call sets. Sets informally are just collections of things. So all the numbers are sets, all functions are sets, all spaces and groups and rings and whatnot are just sets. And sets, we have to be careful of what we mean by sets. So a set is a collection of things. However, we cannot take any reasonable sounding collection of things and claim it as a set. This is what is called naive set theory, and this leads to contradictions. And we'll give an example of one of those later in this video called Russell's paradox, and we will give an example of a reasonable sounding collection of things which is not a set. And we'll explain why it cannot be a set within our axiom system. So, uh, so I gave three things earlier: sets, statements, and predicates. So in math, all our claims, theorems, and whatnot are statements, which are either true or false. And every statement which I talk about can be phrased using first order logic. So there's a system of rules for which we can create what count as well-formed statements. These well-formed statements are always either true or false. We don't necessarily have the ability to prove that they're true or prove that they're false, but they always have a truth value, which is true or false. I'm using binary logic here, using the axiom of the excluded mill, if you've heard of that. And there are also things called predicates, which are like statements, except they have sort of free variables in them. So, for example, I can have a statement of the form x equals y. This is a predicate with two free variables, x and y, and it is claiming that x equals y. So I could write p x y is the claim that x and y are the same. So I could substitute in two things for x and y. These things will be set because everything in math is a set, statement, or predicate. I cannot substitute in statements into these things. So I can check if these things are the same by, they will be the same. This predicate will be true given the two things if and only if the two things are the same. So there's a bunch of rules for constructing statements which we know are allowable, and there are a bunch of rules for deducing which statements follow from other statements. I don't plan to go into detail on the deduction rules because honestly, I don't have a very good formal understanding of all the deduction rules. However, as a mathematician, it's important that you know how to make deductions which are valid from previously defined statements, and there is a finite list of rules for which you can do this. But for now, I just want to talk about which statements we want to be true, and I'll sort of use an intuition-based understanding of how to deduce truth from other statements. Okay. So, for example, I could say if x equals y and y equals z, I would deduce from this that x equals z, and I would be using a deduction rule from this, but I don't want to go into the details of explaining like which deduction rule is doing this because then the video will be like too long and complicated. And I don't want to do a lot of sort of background research on the formal names of all these things. But what I do want to know is which statements do I accept to be true as axioms. So first, an axiom is a statement which I accept to be true without any proof. And every when I have a proof, what this means is I have the ability to construct a sequence of statements, each of which is either an axiom or which I can deduce from my previous statements, and such that I have written the statement I want at the end. And this is the proof of the statement. Every statement that we talk about later on will be provable, and everything I claim to be true will be provable in this way using the axioms I'm about to give out. I will not always write out the proof in this way as a list of statements. I will write out sort of more natural language proof. The idea is that you can convert the natural language into formal language, and I will explain as I write the axioms how to express those in a more sort of formal first order logic sense. The idea is you'll eventually get used to the idea of thinking about which statements are valid, and then we don't have to write them in first order logic all the time because it's sort of tedious and unnecessary. So without further ado, let's start with the axioms. So there are 10 axioms roughly. Two of them are actually axiom schema, so they're sort of collections of axioms. I'll talk about those in a minute, but there are the idea is there are 10 assumptions that we want to make all the time, and we will use these in order to make deductions. So the first axiom is my favorite axiom. This is the axiom of the empty set. So this says in natural language, there is a set with no elements. Okay, and this is the first thing we want to assume. We can write this in first order logic as follows. So this means there exists x such that for all y, y is not an element of x. So this is the sort of first order logic way of writing this. So there exists x in the context of ZFC, everything is a set. So this is saying there exists a set x such that for all y, so for all things, y will also be a set. That's not that important right now. And this is y is not an element of x. So this symbol here means element of. If I put a line through it, it means not element of. So this is saying there exists a thing such that for all things, that thing is not an element of the thing. So this thing has no elements. This is how you write this in first order logic. First order logic is constructed of these existence and these existential and universal state quantifiers. This is the for all quantifier. I have some variables to work with, and I can use equality. I can use this element of symbol because I'm working in ZFC, which has this element symbol given to it, and I can write brackets and or and whatnot, and that's basically all the things I can do. They have to be formulated in like a reasonable way. I can't write this, for example, because it makes no sense. There's no like quantifier. There's no like variable to go after this existence quantifier. But basically, the valid statements are the ones I can make using these constructions. Okay, so that's the first axiom. We have an empty set. This is my favorite axiom because I like the empty set. Okay, second axiom. I should point out that these are not in like any sort of important order. You can reorder the axioms, but this is I'll give them sort of a fairly reasonable order. Okay, the next one I want to say is the axiom of equality, which tells me when two sets are equal. So two sets are equal if and only if they have the same elements. So this is what I call the axiom of equality. I can write this in first order logic. So for all things x and y, I know that x equals y if and only if, this symbol means if and only if, so these things are equivalent. If and only if for all z, or for all z, I know that z is in x if and only if z is in y. So when I think of these sort of logical statements written in plain English, the important thing is that you can check it's a valid statement because you should be able to write it in this form in sort of first order logic symbols. I don't typically think about things in first order logic symbols like this, at least not consciously. I usually think more in terms of this consciously, but it's important to be able to go back and forth between these things so that we know which things we can like logically deduce from other things. So this is saying that for all things x and y, x and y being the same is equivalent to for all things agreeing being an element is the same. So later on in other videos, we'll be proving sets are equal a lot. And the way we prove this is by checking if they have the same elements. So using this condition. So this is the axiom of equality. The third axiom I'll give is the axiom of pairing. So this says if I have two things, I can construct a set which has exactly those things as elements. Using two in the loose sense, they might be the same thing. So if x and y are sets, then there is a set which has uh, x and y as elements and no other elements. Okay, so let's write this in first order logic. I'm not going to do this for all the axioms, but I'll do it for the first few. So this is saying for all x and y, there exists a z such that for all a is in z if and only if x equals a or y equals a. So this is saying being an element of z is equivalent to either being x or being y. This set is usually written like this. Oops. So this is saying for all x, y, this set exists. This is the set of things which has x and y as elements and has no other elements. A thing that is important to understand about sets, you learned early on, is that the order of the things in sets is not important. Here, I told you what it means for sets to be equal. It means they have the same elements. So this is the set which has x and y as elements. So this is the same as the set which has y and x as elements because they have the same elements. They have x and y and they have nothing else. So set axiom 3 is just saying that this set exists for all choices of x and y. I said x and y are sets because sets are the only objects in mathematics. We also have statements and predicates, but these are not thought of like objects, which can be elements of sets. Okay, statements are like things about sets. Okay, let's go into the next one. Axiom 4. Oops. So this axiom, I'll do, what do I do next? I'll do the axiom of foundation. This axiom says if I have a set, I have an element of the set which is not, which is disjoint from the set. So, sorry, a non-empty set. So if X is a set which is non-empty, so it has some element, then X has an element disjoint from X. So here disjoint means it has no elements in common with X. So this axiom here is just to prevent sort of infinite nesting of sets, which can get sort of messy. So for example, there is no set like this uh, equal to the set containing itself, because this thing is not disjoint from any of its elements. Its only element is itself, and it is not disjoint from itself because it is itself is an element of both it and itself. So this is not allowed. We don't want these infinite loop things like this. This tends to cause paradoxes, and we not only like I mean we don't need to assert that this doesn't happen in order to prevent a paradox, because that's not how paradoxes work. If we could make a paradox, then having this thing would only force it to like actually be a contradiction. The idea is we have this axiom because it will help us in avoiding things which we know are not supposed to happen in certain specific contexts. You can actually do most of mathematics without asserting this, but uh, yeah, I want to assert this because I use it a little bit in uh, in some things. So there's a thing called the von Neumann hierarchy I want to talk about later, which uses this importantly. But most things don't need this, but this is basically you don't want sets to contain themselves. That's just not a thing that ends up working nicely usually, and this prevents that from happening. It also prevents other things from happening, but yeah, it means things are sort of reasonable. Uh, we have some sort of foundation for everything. Okay, so the next axiom I want to talk about is let's see. I'll do the axiom of union next. So this is it says if I have a set of things, I can take their union. So if X is a set, then the union of X is a set. This is union. So does this mean? This is the set of things which are elements of X. So this is set of elements of elements of X. So I could take, say, the union of X, Y, and Z. This is a set of sets, and this has got the elements of this is X, Y, and Z. So if I got some things, I can stick them together like this. And this could be an infinite family of things if I wanted as well. So I have any set of things, I can look at the set of things contained in those things. This is called their union. Okay. So next one. This union symbol is going to be useful a lot in other videos. Like this is a thing every mathematician knows this union symbol and uses it like all the time. Okay, the next one I want to talk about, I'll um do the axiom of the power set. So this is a nice axiom because it lets us make big sets later on. So this is the uh, every set has a power set. This is if X is a set, then the power set of X is a set. This looks a lot like the predicate symbol. So this is uh, I'll just write it in words. Then the power set of X is a set. So what does the power set mean? This is the set of subsets of X. Is the set of subsets of X. So if I have a set, I can look at all the sets which are contained in X as subsets. A set is a subset of a set if all its elements are elements of the set. So for example, uh, this set here, this is a subset. The symbol means subset of this set here, where X and Y can be anything, because every element of this is an element of this. The converse is not necessarily true unless Y equals X. So in the situation, every element of this is an element of this. So if I look at the power set of this set, it includes this as an element. So uh, the set containing X is an element of the power set of X, Y. This power set is usually noted with this P symbol here to the left. So this is an element of the power set of this. So if I have any set, I can take its power set. And the power set of a set is usually much bigger than the set in question. In fact, it's always bigger than the set in question, even if the set is infinite. We'll talk about that later, but it's usually like a lot bigger than the set in question. Okay, so yes, the next axiom I want to talk about is the axiom of infinity. We're getting to the more sort of messy ones now. So this basically asserts that we can do infinite sets. But how do I do that? There's lots of sort of equivalent formulations. I'll give the one which will be useful to me later on. It's sort of, I think the most natural one, which doesn't require a lot of background things. So, uh, okay. So first, I want to talk about the sort of successor thing. So first, if X is a set, then we define the successor thing of X plus, to be X union the set containing X. You can use the axiom of pairing and the axiom of union to prove that this exists all the time. So this axiom says is there exists a set let's say n, it's going to represent the natural numbers, uh, such that the empty set is an element of n. This is the symbol for the empty set. This is the set with no elements. You can see from the axiom of equality and the axiom of the empty set that this exists and is unique. The axiom of the empty set says that there is a set like this. The axiom of equality will tell us that there's only one set like this because any two sets with no elements have the same elements. And this is the symbol we use to denote that set. So I'm saying the empty set is an element of n, and for all x in n, the successor of x is in n. This basically lets us take a set and create an infinite construction in it, because this will contain the empty set, it will contain the empty set plus, the empty set plus plus, and so on. So this gives us an example of a set which is infinite. We cannot prove the existence of such a thing without asserting it as an axiom. This is the axiom of infinity. N will be the natural numbers later. We'll talk about that. Yeah, when I do more ordinal stuff. Okay, so there's three left. The three left are sort of the messy ones. So two of these are actually axiom schema. They're not axioms. I'll explain what I mean by that in a second. The other one is the axiom of choice, which I want to do last because it's sort of controversial. I say it's controversial. It's not actually controversial, but a lot of people say it's controversial. Maybe I shouldn't say that, but it's like in modern mathematics, it is generally assumed that you're using the axiom of choice unless specified otherwise. Although some people like to specify otherwise, and this is fine. But before that, we'll do the axiom schema. So this is the first axiom schema. This is the axiom schema of specification. So it's an axiom. It's a different axiom schema. So it's an axiom schema instead of just an axiom, because um, I'm not making I cannot state this as a single first order sentence. The other things can be converted into first order sentences, as I was doing earlier. But this one cannot be converted into a single first order sentence. It's a family of them. So first, what I say is if P of X is a predicate, so this is some property of the set X, which I can define using the relations and logic rules I've mentioned before. So I can use ands and ors and exists and for alls, and I can use the element of symbol. So this is a predicate, and uh, say, let's use capital X is a set. Then I can use what's called set builder notation. So then the collection of all things X and X such that P of X is a set. So this is the set of all elements of X which satisfy this predicate. So if we had like numbers available to us, this would tell us if we have a set of all numbers, we can look at the set of even numbers, for example, because being even is a predicate, which is definable. So this says I can take any set I want, X, and restrict it to just the things which satisfy a certain property. And this is not an axiom, it's an axiom schema, because for each property, I need a new axiom. And I cannot have a sentence about sentences. First order logic did not let me do that. So for each predicate, which is basically a sentence, but with a free variable, I have a new axiom saying that for all sets, I can restrict them to the elements of this thing. But it is reasonable to think of this as one sort of assumption, which is why it's given as like one point in my list of 10 conditions. So this says, so whenever I've got a set and I've got some reasonably definable condition on it, I can restrict the set to the things with that condition. This is the axiom of specification. It is usually denoted like this. Okay, the next one is the axiom of replacement. This is also an axiom schema thing, which is why I left it near the end. So this is saying if I have a binary predicate, which is often thought of as a relation, I'll call it R for relation. So if Rxy is a relation, a predicate, I'll call it a predicate. And for each x, there's at most one y satisfying this, and for all x, there is at most one y with Rxy true. So Rxy will be true or false depending on what x and y are. So this is saying that for each x thing, there's at most one y thing satisfying this. And this is, and if I have a set x, then I can look at this set. The set of all things y such that there exists x in x with R x, y. There's lots of equivalent ways of doing this schema, but this is how I like to do it, is a set. So this says if I have a set x and I have a way of relating each thing in x with at most one other thing, then I can replace x with all the things related to the things in x, and this is a set. Okay, so if I say it for if I have some way of defining for every number some nice set I want, then I can just look at the set of all of those things because that like the numbers form a set, and I can replace each number with the thing. This is the axiom of replacement. Basically, if I have a set of things and I have another thing which I know are like in correspondence with those things, then I can look at those things as a set as well. Okay. And the last one is the axiom of choice. Number 10. Axiom of choice. So this says it gives me a way of constructing functions, which I call choice functions. So I haven't defined what a function is because this is the foundations video. I will define what a function is in another video. However, I want to give you it the way it's usually stated. I imagine most people know what a function is. If you don't, you can wait until the other video to understand what's going on. But this says if X is a set of non-empty sets, so each set, if every element of X is non-empty, then there is a function C, which I'll if C for choice, with domain X. So this is a function. It takes any element of X and outputs a thing, such that for all X in X, X, C, I use right actions. I like to put my functions on the right. So this is the function C applied to the element little x of big X. So this is an element of X, which makes sense because X is non-empty. So this is saying if I have a set of non-empty sets, I have some way of assigning to each of those sets one of its elements. This is called a choice function. And I'll define formally what a function is later, but for now, I mean, informally, you can think of it as a way of choosing things out of a way of mapping things to things. So for each of these little x's, I can map it to a thing, and that thing I map it to will be one of its elements. This is why it's called a choice function. So for example, if I look at this set, uh, x, y, z, a choice function could be as follows. I could choose to map x, y to y, because I'm choosing y from x, y, and I could choose to map za to z, choosing z out of z and a. So this choice function is choosing z from this one, and it's choosing y from this one. And I can do this for any set, including like really big and infinite sets, and that's what the axiom says. And that's all the axioms. So if you accept the things I've said is true and meaningful, then everything else I say should be totally legit to you, assuming you're okay with my deduction rules, which I did not explicitly format. So now I want to give you a sort of example of a proof, which I think is an interesting proof and one does not require a lot of background information. And it gives you an example of how proofs works, and it sort of gives you motivation for why we need to be careful with which sets we can make. So now I've told you a bunch of sets I can make. I've used axioms to say in these situations I can make sets which do this. If we just use naive set theory, where we say we can take any collection of things we can reasonably state and call it a set, we get contradictions. And here I will prove to you that there is a reasonable sounding thing which is not a set. A reasonable sounding thing, which is not a set, is often called a proper class. So a class is a way of referring in set theory to all the sets which have a given property or satisfy a given predicate, and some of these are not sets. So there are some predicates such that the things satisfying the predicate do not form a set. And I want to give you the first example. So this is sort of Russell's paradox, which says uh, there is no set which contains all the sets. So the way a mathematician would probably say this is the sets form a proper class. The class of sets is not a set; it is a proper class, meaning it is not a set. And I will prove this using only the axiom I've given to you so far. So proof. So I'm claiming something does not exist, and I'm going to use what's called a proof by contradiction. So if we want to prove something by contradiction, we take the statement we want to prove, and we assume that it's false and try and reach some nonsense out of it. And this will mean our original assertion must have been nonsense as well. So suppose for a contradiction that there exists a set X such that for all Y, Y is an element of X. This is the negation of this statement written in first order logic. So there exists a set which has all the sets as as elements of it. So this written in first order logic, there does not exist a set X which has all the things in it. So I want to reach a contradiction from this. So now I have the set X, I can start using it and I can start applying the axioms to it. So by the axiom specification, and this is the axiom schema, by the axiom schema of specification, I can define a new set, and I will know it's a set because X is a set. So this is B for bad. B is defined to be the set of all X in big X, which is all sets, such that uh, X is not an element of X. This is a well-defined uh, predicate, X not being an element of X. I'm allowed to use negations, and I'm allowed to use the element of symbol. This is a well-formed predicate, so I can use it with the axiom of specification. Because now if I assume X is a set, which I just did, then I can conclude from the axiom of specification that B is a set, and I'm going to reach a contradiction. So I know either B is an element of B or B is not an element of B. Because these statements are negations of each other, and each of them are well-formed statements. One of these must be true. This may sound like I'm talking about the axiom of foundation here, but this proof actually does not use the axiom of foundation, although you could try and work it in if you wanted to. We can reach a contradiction without foundation. So yeah, I'm going to reach a contradiction in both of these cases. So there are two cases. I will prove that in each case there is a contradiction, and so there will be a contradiction. So if you want to prove something from an or statement, you assume each part of the or statement and then conclude what you wanted to conclude in each case. So, so case one, if B is in B, then that means, by definition, that B is an X, because X is the set of all sets, remember? And B is not an element of B, because by definition, B is the things which are not elements of themselves. And this is a contradiction, because I said B is in B here, and I said B is not an element of B here. So this is a contradiction. I'll often write this symbol to mean I have reached a contradiction. So case two, B is not an element of B. And now I want to reach a contradiction. So then either B is not an X or uh, B, let's write this sort of more carefully, or so either it fails to be an X or it fails the condition we use to specify the elements of X in B, or not B is not in B. So here, being an element of B means that you're an X and you're not an element of yourself. So if B is not in B, then either B is not an X or B is not an element of itself. So this is impossible because every set is an X by assumption. So this is false. And this not B not an element of B. So this means B is an element of B because this is not, which is false because I just said it was false here, which is false. So this is false or false. So this statement is false. And I have a contradiction. I've just proved a false statement. So in either situation, I have a contradiction here. I did not use axiom of foundation. So I have reached a contradiction in all cases. So both B and B and B not in B are false, which is a contradiction in the end. One of these must be true, and they're both false. And the only assumption I made was that X is a set, which means this assumption must have been false. And that's the end of the proof. So now we know there's a set, there is no set which has all the sets in it. We do know we have lots of sets, that we have the empty set, and we have all the sets we can make from the empty set and the other axioms using the other axiom. So we have this empty set, we have this set we got from the axiom of infinity, and every other set we make is going to be made out of those sets and the other axioms. Okay, so I hope this gives you a good basic starting point for set theory. And from this point on, we want to define all the mathematical objects we know and love using sets, and we want to prove things about them. They will all be defined using these axioms, and all the things we want to know about them will also be proved using these axioms. Bye bye.